Greetings all. In the last lesson, I introduced the one-sample t-test and used it as an example to discuss the three major components of inferential statistics: testing for statistical significance, effect size, and confidence interval. In this video, I'm going to show you how to conduct a one-sample test of proportion, following the same 5 steps of hypothesis testing as in the one-sample t-test. A one-sample test of proportion is used to assess whether a sample from a population has a proportion that is different from a known or hypothesized proportion of the entire population on a binary outcome measure. It's easier to understand this with an example. Let's assume that a university administrator needs to convince the board of trustees that the campus recreational center needs renovation and upgrades. The board of trustees will only agree to fund the project if more than 60% of students support it. A random sample of 200 students is selected and asked their opinions. Of those, 128 voted yes and 72 voted no. First, we need to understand that this is a directional test because the researcher is hoping for a proportion greater than 60% or 0.60 in proportion. So the null hypothesis is H0 P lower than or equals 0.06, which states that student support for the project is no more than 60%. The alternative hypothesis is HA P greater than 0.60, which states that more than 60% of students support the project. Here, the uppercase P represents the proportion of students supportive of the project in the population. In step 2, let's go with alpha equals 0.05. Again, please know that the sampling distribution of the proportion is a framework. If we were to take all random samples of 200 students from the university population, and each produced a proportion of support, all the proportions would form a sampling distribution. With a large enough sample, this distribution adequately approximates a normal distribution. Note that the sampling distribution would instead be a binomial distribution if the sample were small. So how do we decide whether a sample is large enough? We check the product of the sample size n and the proportion p, as well as the product of n and 1 minus p. As long as the smaller of the two products is greater than 5, the normal distribution can be used as the sampling distribution. In our example, with n equals 200 and p equals 0.60, this condition is met. In step 3, we calculate the observed statistic and find its p-value. The formula is Z equals the difference between the sample proportion and the population proportion over the standard error of the proportion. The standard error of the proportion is calculated as the square root of the population proportion p times 1 minus p over the sample size n. Based on the sample information, we find that the square root of 0.6 times 0.4 over 200, which is 0.0346 for the standard error of the proportion. The sample proportion is 128 over 200 equals 0.064. The observed z-score is the difference between 0.64 and 0.60 over 0.0346 equals 1.155. Using this z-score, you can look up in the table that the probability of obtaining a higher value is 0.124. Alternatively, you can find that the critical z-value is 1.645 for a one-tailed test. In step 4, based on the evidence that the probability of 0.124 is greater than alpha equals 0.05, and the observed z of 1.155 is smaller than the critical z of 1.645, we fail to reject the null hypothesis. So what is the conclusion? A random sample of 200 students was selected, of which 128 were supportive of the renovation of the campus recreation center. However, given alpha equals 0.05, the proportion of support was not significantly higher than 60%. To provide a range estimate of the possible support rate, we proceed to construct a confidence interval. With alpha equals 0.05, the 95% confidence interval is the sample proportion plus minus the critical z-value times the standard error of the proportion. So we have 0.64 plus minus 1.96 times 0.0346, giving a confidence interval that ranges from 0.572 to 0.709. Because the population proportion p equals 0.60 is within this range, our decision not to reject the null hypothesis is validated. I use this example of a directional hypothesis to show you that for a one-tailed test, the critical values for hypothesis testing and for constructing the confidence interval are not the same, even though the level of confidence equals 1 minus alpha. Although it's a directional hypothesis, when building a confidence interval, you must always use the two-tailed critical values. This is because the region of rejection for the null hypothesis in the one-tailed test lies only in one tail of the distribution, whereas the confidence interval is constructed symmetrically around the observed sample statistic.